Hello everyone, this is Amir from Audio Science Review. I have another product review for you. It's somewhat of an unusual product from company CHORD called the Hugo M-Scaler. As the name kind of indicates, it takes digital input and outputs digital audio, but it is able to upsample it to a higher sample rate, either twice as much, 4 times as much, or 16 times as much. And the idea is that the larger that number, the better it can make your music sound. And company's claim to fame is that this upsampling uses very, very large filter tabs. And I'm not going to get into details of what that is right this second, although I'll show you some measurements and talk a little bit about it. There is a theoretical benefit in that you can make a filter sharper in response if you have more taps. And company claims that the more taps they add, the better the sound fidelity is. And even though the difference can be measured down in, I don't know, 300 dB or so. So very, very incredibly small numbers. But anyway, our job is to forget about what's inside the box and say, well, you know, how does it work as a solution, as a black box, if you will. It's typical of CHORD products with these globe plastics that light up different colors. Let me get that. It's quite heavy in this instantiation of it. And I usually detest the interface because you have to memorize what the buttons do, and on top of that, what the different colors mean, and so forth. Here, there are a lot of them. And that makes it easier to learn what the buttons do. And so I didn't have as much difficulty, although I had to memorize the sample rate conversion colors. At the beginning, I had to keep looking at the manual to know what, you know, red and blue and white were. So, you know, not the best thing in the world. And certainly at nearly $6,000 price, I expect to see a display on this and showing me what it's doing as opposed to trying to memorize what these buttons are. If you look at the back of it, you can get a better picture of what it does. It has a set of digital inputs, so you can have 2 different SPDIF in the form of BNC inputs. Typically, you see RCA jacks in here, but the more correct way to implement this is using BNC as far as impedance. You have a couple of Toslink inputs, and nicely, it has a USB interface. So if you plug this into a computer, this actually acts like an audio device, even though its output is only digital. So you still need a DAC to connect to the downstream. And the DAC you can connect with a Toslink, again, optical, or you can connect with a coax as a single channel SPDIF. But you can also connect it using dual cables with a proprietary scheme that CHORD has come up with that only works with their own DACs. And if you did that, you can way exceed the spec for SPDIF all the way up to 768 kilohertz. Now, the member was kind enough to loan me a CHORD Hugo 2 also that is compatible with those dual cables. So I managed to go ahead and test the full capabilities of the product with CHORD's own DACs. But the product is standalone. It can also work with existing DACs, and I'll show you the results of that. Very fancy cabling was supplied with it. 2 Nordost Tier 2 cables. Each one of those is $1,800, so I had $1,600 worth of cables alone. Then the Hugo 2 doesn't have BNC or even RCA inputs. It has a 3.5 millimeter connector, so you have to have a Y connector from that to this. So a lot of pieces and a lot of moving parts in here, but bear with me, we'll get through it. A little bit about operation of a device. Whenever you have a digital processing device, you have an opportunity for things to overflow as you apply math and everything. So typically what you do is that you lower the levels to allow some headroom for the math, and then you do your processing there. The problem with that is that now your output level is lower and you actually lose some dynamic range. To make A/B testing of all the different sample rates easier, CHORD has implemented a pass-through mode where it's the, you know, one of the 4 different modes. When you push that, this button goes, oh, sorry, you couldn't see my mouse. This button goes red, and but the pass-through is not a bit perfect pass-through in that it still does this level adjustment. which is nice because then when you cycle through the other modes that actually do the upsampling, then the levels don't change. So it makes it very easy to do A/B testing that way. So I appreciated that. But again, remember, you are losing some dynamic range as soon as you do that, but whatever amount is, I think it's 2.5, 3 dB. And how much you take out is how much you lose in dynamic range. Turns out the situation is actually worse, and we'll get into that. Okay, so first thing I did was just look at the basic quality of digital connections on this. The Audio Precision APX555 that I use has a special option where you can look at the jitter on a digital audio interface, including SPDIF. And so I ran that. First, what I did was to get a baseline and get you familiar with it. The audio analyzer has both input and output SPDIF, so I connected them with the same cable I used later on with the CHORD, and I measured what its input and output measure itself, how much jitter comes out. And I'm running a special test signal called the J-test, which I won't go into, but these spikes are correlated with that. So this green line is the baseline best case performance of the measurement system itself. And then I routed the signal through M-Scaler and tested it in either pass-through or 2x or 4x on this thing. And I was shocked to see this much increased noise floor over here. And not only do we have this increased noise floor, but now these jitter components are actually now riding on top of the increased noise. You would think if it just a noise went up, it would just swamp these jitter components, but it didn't. It also raised those. So this is shocking because companies tend to build or over-engineer products in ways that typically don't have value, but they don't do any harm. In this case, it's under-engineered in that it is clearly adding noise. And this is either jitter, random jitter noise, or quantization noise, meaning the internal precision and or the dithering that it does, and I'll get into what dither is in a minute, has robbed you, some amount of performance. Now, we're still talking very small numbers. If you look at the scale in here, this is 1 picosecond. So this thing has gone from 1 or 2 picoseconds now to 12 or 15 picoseconds. So it's not audible stuff, but for a company that prides itself on engineering and precision of its filtering, this seems quite sloppy work. I can get a $100 USB to SPDIF converter, and it will perform better than this. And by the way, this is with USB going into M-Scaler, and I'm testing the coaxial output. But what happens if we take the clean signal out of my analyzer in SPDIFs and output SPDIF, so SPDIF to a SPDIF converter? The problem gets far worse. Now look at what's happening here. We still have our much raised random noise floor, but we now have this really correlated spikes that are very, 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 very distinct. One of them is now shooting up to almost 2 nanoseconds in here. So about, 1,000 times higher level if you use SPDIF input. That was just shocking to me. So I went to the dashboard view where the analyzer also has a jitter meter, and I asked it to show me the jitter when I'm not using the M-Scaler, and this is as low as it can show, by the way. It's showing 214 picoseconds. It's actually much lower than this, but the meter doesn't have lower resolution. But when I ran the same signal through M-Scaler, look at this. Now we have 4 nanoseconds. Every nanosecond is 1,000 picoseconds. So we have about 20 times more jitter coming out of M-Scaler than without. And it's just shocking to me. I mean, this is almost a $6,000 digital device. Doesn't have any analog circuits in it, doesn't have things that normally would be difficult and challenging to get right with precision. All this got to do is send out a clean signal over a SPDIF, and it's clearly polluting the input signal. Now, DACs are very good at filtering these kinds of noise. So as a practical matter, you won't hear it, but hey, if you're going to sell me an expensively engineered product and you're selling it on precision, then it better not, destroy the input as far as fidelity of signal. And a lot of audiophiles go chasing, cables and all kinds of tweaks to reduce jitter. And here we are, an audiophile tweak device that is just putting copious amounts of jitter in here. Just to give you context, about 500 picoseconds is equivalent of jitter is equivalent to 1 bit of a 16-bit audio. So this is like 8 times more than that. So you've clobbered 2 or 3 bits of 16-bit audio if you can't filter this jitter. So even though it's a small number, its impact can be fairly large. If you still have doubt visualizing what this looks like, if I look at the jitter spectrum of the analyzer output before it goes to M-Scaler, look at what it looks like. It's basically random noise, a little ticks in here and there. Now look at what happens when I run it through M-Scaler. You can clearly see a pattern in here, which means that noise is bleeding from rest of the device onto the coax output that's coming out of it. It's just unacceptable. I know the company and the designer, Rob Watts, has an audio precision analyzer, just like I have. You would think he would have measured this and just for sake of good engineering, trace this down and fix it. I don't think it's a complicated problem to fix, but maybe he didn't measure it. Maybe he doesn't know how to measure or care about jitter. It's puzzling to me. It's just totally out of character, and it just doesn't make sense in this class of device. Hey, if it was a $500 device, I expected to not do this, let alone a $5,000 device. So this is just looking at fidelity of that coax signal. And by the way, as I mentioned, depending on, it doesn't matter which mode and upsampling you use, you're going to be saddled with this jitter. So it was not dependent on upsampling or not upsampling. It's just physical layer issues with the interface that it has. Next test I did was connect the M-Scaler to a topping D70S. Before I show you that, let me show you its performance standalone and driving it with coax, because that's how I'm going to drive it with the M-Scaler. And you can see the incredibly good performance it has. The only distortion it has is well below threshold of hearing. And Cyanid's 118 dB. It's just fantastic. Now note that it outputs 5 volts by itself. Now I run the same signal through M-Scaler, and let's see what happens now. The output drops to 3.6 volts. As I said, it tries to create a headroom in there. We're still in pass-through on M-Scaler, which means that it's not upsampling anything. All it's doing is changing the level in theory. But look at what happened to our Cyanide. It dropped like a rock from 118 down to 96. Again, I have the M-Scaler in pass-through mode. The only thing it's documented to do is change the level. No way I should be losing 25 dB of performance. And why are we losing that performance? Is because of this spectrum. Look at all these spikes that are here that we did not have before. To the left of our tone, there was nothing, completely blank. Now we have this oddball thing at around 310, 320 hertz. What's the cause of that? I mean, that doesn't relate at all to the signal I'm testing or anything. These other spikes are not harmonics at 1 kilohertz. This one is not 2 kilohertz. It's like 1.6 or something. They're all at odd multiples of each other, but not related to the main tone, which is just 1 kilohertz. Your guess is as good as mine as to how I did this. I actually retested this 2 or 3 times. I connected direct, and I got this performance up here, as expected. And I go through M-Scaler in bypass mode, and it's doing this to the DAC. It just makes no sense. It's creating some kind of incompatibility, overdriving the inputs on topping D70S. Whatever it's doing, the variables, the M-Scaler doing this. So even though the company says you can use this box with other DACs, I'll caution you in doing anything like that, because God knows what your DAC is going to do. Here, we've lost performance all the way down to 16 bits now. 25 dB of hard-earned performance in the design of the DAC has been thrown out the window. So, this was very unexpected. You get a box like this, if you're very, skeptical, you could say it does nothing. Well, it's doing serious harm in here. And it's not because of jitter, by the way. As I explained, jitter's filtered out, and these are not jitter components on this thing. So let's go ahead and switch DACs now, use company's own DAC, Hugo 2. and same pass-through mode. We see that it drops its output. I'm not showing you its full output, but it also takes its output from 2 volts down to 1.5 volt. But now none of those problems are apparent. Clearly, the companies tested it with their own DACs, and there are no issues there. But, you know, with just a random DAC that I picked, it was clearly doing some damage there. So now we say the next question is, okay, with their own DAC, nothing bad happens, but is there some good happening? So I went ahead and applied 2x upsampling. So my 44.1 kilohertz is now 88 kilohertz. And then 4x upsampling, which is 176 kilohertz. And if you compare these together, you see that upsampling buys you nothing in here. Basically, we have run-to-run variations in SINAD. And the distortion is the same. You see the same 2 spikes in here, same 2 spikes over here, the noise floor. Not a hair's out of place on this thing. Now you might say, whoa, you know, maybe only at this dual cable mode is where the magic is. All right, well, let's look at the dual cable mode. This is a dual cable mode, so it's running at 760 kilohertz, whatever that is, 16 times 44.1. And guess what? Same 2 distortion spikes, same noise, same output levels, same frequency. It just, nothing's changed. Nothing is changed. The DAC still thinks it's being fed the original signal, if you will, with this test dome. So testing all 3 modes, 2x, 4x, and 16x, in our dashboard view, there's absolutely no difference in distortion, noise, or anything else that you would think that this, you know, magic is happening. And I have more tests to show you. But let's step back and say, is it doing what it says it's doing on the label? And the label says I use these very, very large tap filters, which, by the way, cause a lot of delay. So it has this hokey video mode that's supposed to reduce that delay if you watch video, and it only works at 48 kilohertz, so it's not a good solution. But anyway, indeed, it is doing that. So if I go back to the topping D70S and test it with its own standard slow filter, by the way, this is 48 kilohertz, not 44.1, so I forgot to change the title. We see that 24 kilohertz should be our cutoff thing, but most DAC filters are lazy in that regard, so it goes up to 26 kilohertz before it, you know, gets to its full attenuation. When I switch to 2x or 4x mode, and look at what I get. By the way, the bypass is the, you know, same, although there's a noise increase in here, which I'll get back to. When I go to 2x and 4x, look at what happened. I do get this sharp filter as promised. So yes, it is giving me the more perfect reconstruction filter that a DAC requires at half the sampling rate. So it's at 48 kilohertz, we go to 24. So it is doing that. But look at what happened here. The noise floor has sharply increased. This is the noise floor of the DAC by itself when it's being dragged. But as soon as I run the signal through M-Scaler, whether I'm in bypass mode or 2x mode or 4x mode, I've now lost a good bit of noise floor over here. So the device is clearly adding noise. Now this is the analog output. I'm no longer showing you jitter spectrum, which I showed you before. This is a true analog waveform that would go to your amplifiers and will arrive at your ears. And we've lost that. And that noise floor now is not impressive at all. So we've got, I don't know, 80 to 90 dB of noise reduction, attenuation, which is poor. If I had a DAC and I tested its filter and only had this much attenuation, I would give it a thumbs down. So it's not good. You want to get a high-performance DAC, needs to really filter out this stuff, not let all the junk through to infinity at this raised floor. I should say that somebody posted a stereo file measurement of the same device, and their number over here is -120, and people said, whoa, you know, your measurement's wrong. Actually, it's not. If you look at the stereo file, they did not zero out the reference. So their reference is -40, and then attenuation is -120. Subtracted from each other is only 80 dB. So their measurements are 100% consistent with mine. So know that and not discuss that in the measurements here. Now, something that could change the tonality is frequency response. So I've created a very high resolution measurement where you can see here a frequency response, and it's only half a dB down on each side. So this is extremely zoomed. And on the frequencies, I zoomed into where the transition band is. You can see that in a bypass mode, the DAC truncates to at about 21.7 kilohertz. So more than good enough. The audible band's about 20 kilohertz, and most of us can't even hear that. So the DAC didn't need any help. But as soon as we go through 2x, 4x, and 16 upsampling, we see that we no longer have that truncation because the DAC is operating at a higher sample rate. So the response actually keeps going. But in the audible band, in here, the dashed line is the bypass mode, and the 2x, 4x, and 16x, which I've tested here, all of them have basically the same output level. They're just maybe a 0.01 dB difference, but I'm not worried about that. So there is no frequency response difference, which means that anybody who claims the bass is stronger or the treble is smoother and all that, it's all bogus, because the tonality has not changed one bit between all four modes of this scaling device. Now, one of the cool things about the bypass mode, as I mentioned, is that it brings the levels down, so therefore it matches it to when it's being processed. And with the Hugo 2 DAC, I'm able to switch between bypass and 2x without a glitch. So as you listen to music, you just hit it and instantly you're upsampled and there's no interruption. And using that, I did a bunch of listening tests to my standard tracks that I have, and I used my Dan Clark Stealth headphone, which is a $4,000 headphone, state-of-the-art as far as tonality and distortion and so forth. And I could not hear any difference whatsoever as I was doing. I mean, it was just as transparent as you could get. Unfortunately, when you go to 8x or 4x or 16x, all of a sudden the DAC would pause for almost a second, and then it would start playing. And that glitch is enough to completely destroy your short-term memory and invalidates any comparison between bypass and those higher modes. I wish there was true random access between those and also no delay. I mean, it would be nice if the bypass mode also did a delay so that the delay was constant and you never had the glitch, but it's not that way. Now, I know when I say, well, I didn't hear anything, people will say, well, you wanted to not hear anything, which is fair. So what I did was that I made two captures with my RME ADI2 Pro FS, and I've got those on Dropbox. They are linked in here, and they're blind in that I'm not telling you which one's which. There's sample 1 and sample 2. You're welcome to listen to them to see if you can tell the difference. Tracks they've been up since I did this review yesterday, and at least one person tried to listen who was an advocate of M-Scaler, and he couldn't hear the difference. So now the arguments come back that, how about 16x and everything? My simple answer is, look, bypass mode has none of this magic filtering. As soon as you go to 2x, it's got a very high tap filter. If that difference, that stark difference, has zero audibility, good luck in making a case of this thing being audible. So samples are there. You're welcome to go listen to them. I thought about playing them here, but going through YouTube and compression is not a fair thing. So go and listen to them and see if you can guess which one's which on this thing. So where are we with this? We got a box that I expected going into the review to be doing is upsampling more perfect than you possibly could imagine, but probably not an audible difference. What I found was very disappointing, that it objectively lowers the fidelity of the signal. It's got noise and jitter on its SPDIF output. It gets better if you use USB as an input, because USB doesn't, clocking is different. But if you use coax input and coax output, you're really going to suffer on that. Again, probably not an audible thing, because the DAC, any decent DAC, will filter that. But why? Why $6,000? It clearly raises the noise floor in its filter, and its filtering is very precise in frequency, but sloppy in amplitude. And we need the amplitude to be more perfect than we need the frequency to be perfectly vertical on this thing. And so very disappointing from engineering point of view. Now, the company designer, Rob Watts, put out an answer to my review, and he quickly accepts and admits that the noise is higher, so what? You won't hear it. It's like, well, excuse me, people buy these boxes, live and die by reducing noise and EMI this and jitter that, and here you have noise that's been generated, and yeah, first of all, you didn't tell anybody. He's got 2,876 posts in here. Waited for me to find out that there's noise issues there. And where is the noise coming from? I explained that whenever you do math, you're going to have a new set of results. If your internal representation has higher resolution than the data that you're trying to process, as it should be, otherwise you lose a lot of accuracy, ultimately, you still have to convert things back to integer 24-bit PCM samples coming out. And to do that conversion, you can't just truncate the high resolution numbers to get the low resolution. You need to apply what's called dither. And dither is just basically randomization of the bits in a special way. And if you do that, you don't get distortion, but you get extra noise. So right away, there's a problem with this architecture in that no matter what this device does, it will always add extra noise to your audio signal. That's a guarantee because, you know, my measurements show it, and the designer says that they're adding dither noise. And they have to do this. It's not like he has the option of not doing this, but he has to be upfront in that. Yes, it's a noisier output is what comes out. Don't go assuming that this is from CHORD and therefore is some perfect resampling device. The signal processing fundamentals don't allow it to not add noise. Now, he says the noise is higher than it should be because he uses Gaussian noise as opposed to triangular dither. What this refers to is that, let's say I have one digit, I have numbers from 1 to 10 that have 1 decimal point, so 3.4 rather than 3, and you want to convert 3.4 to just be 3s. Common technique you know about is rounding, right? Anything less than 0.5 you throw away, but anything over 0.5 you add 1 to it. That's actually a form of dither, and it's not a good form of dither. A much better method is to randomize that, lower the bit that you want to chuck. And one of it is a Gaussian distribution, which is this bell-shaped thing that you may be familiar with. And he's saying that's better than triangular dither, which came as quite a shock to me and anybody knowing about signal processing. Triangular dither looks like this, whereas the other one looks like a bell-shaped thing. I hope anybody that ever deals with dither is familiar with this paper from Professor Lipschitz and Professor Van de Kuy from University of Waterloo in Canada. The duo really know their math and signal processing and written tons of papers for Audio Engineering Society on this. And if there's ever somebody you don't want to mess with on dither is these two guys. And indeed, Rob Watts is messing with them because they have a seminal paper, the paper that demonstrated why you want to use triangular PDF dither versus Gaussian dither. And right here, you know, if you don't understand anything I've said, it says this is better than Gaussian dither. Okay, it produces noise that's 1.2 dB less than Gaussian case. So if you use triangular dither, you don't have to add as much noise to the system. Remember, I said you have to add this noise. So better use the best case scenario in here rather than the worst technology in here. Now, as the professors tell you, is that the reason it doesn't get used as much, and by the way, this is an old paper today, it's used all the time, it's because it takes more complexity to generate those numbers. In computers, it's a walk in the park. Every audio workstation lets you apply TPDF dither, not a problem at all. But this product implements everything inside an FPGA, and logics are logic and cost money. So perhaps some cost cutting was involved. But there's no question that Gaussian dither is not as good. Both of these dither systems do the job as far as trading distortion for noise, but you definitely want to use a triangular dither. And the proof is in the pudding. I showed you that there's a noise penalty in device that it should not be on this thing. Okay, so hopefully you got something out of it. In my opinion, this device does nothing useful as far as sonic improvements. Anybody who says otherwise should go conduct a blind test like I did. Have somebody test them blind, do it 10 times. If you get 8 out of 10, just identify which is which on this thing. And absence of that, please don't come tell me you hear the improvement. Yes, I would also hear the improvement if I bought a $6,000 device, hooked it up with all excitement, and paid more attention to what I'm hearing. All of a sudden, I'm going to hear more detail and soundstage and all the classic things. And it seems like just about everything that people think does something when it doesn't, comes back with the same thing of more detail, blacker backgrounds, and better soundstage. So that should be a clue that that can't be true of everything. Anyway, the objective test back what I just said. And while it objectively generates noise and jitter, I don't think that's a degradation, so I don't expect people to be hearing that artifact, and I did not hear it either. But in my opinion, it's not well engineered either. So it's a product. Sometimes you just have to sit back and state it simply that it's not needed. It's not it doesn't improve things for your sound, for audiophile, and he certainly doesn't make it 48 kilohertz or 44 kilohertz music sound like a high-res music. Once you take a high-res music and chop off the spectrum, you can upsample all you want, but you already threw out the information that you can't recreate. Certainly you can't recreate it like this, or we would all be watching DVDs on our 4K and 8K screens and saying we don't need 4K, Blu-ray and what have you. A lot of people think upsampling gives you the original. It doesn't do anything like that. It's a simple filter algorithm, and it never creates more information. Yes, there's some issues with, filter response in the DAC being different at low versus high. But remember, this thing does add, its own poison to the signal path on this thing. Okay, and I can take you to consensus of our forum, see how people voted. Yeah, 91% think, 92% think is not worth anything, and the few characters, said that is great. So I've always given high marks to Rob Watt's DACs. I think they're over-engineered and expensive, but I do recommend them. So it's not an issue of cost. This one just unfortunately doesn't do anything useful other than take out a chunk of change out of your bank account. Okay, see you in a future video. Bye-bye.